So what you are seeing is a white precipitate. It's a white solid. If I should filter this, the white substance you are seeing will be left on the filter paper. And what I've done right now is a chemical reaction. So I added barium chloride to sulfuric acid. The product there is going to be barium sulfate plus HCl aqueous. Then the equation can be balanced to that effect. Now the barium chloride is soluble, so it is aqueous. The sulfuric acid is also soluble in water, so it is aqueous. But barium sulfate is insoluble. Barium sulfate is insoluble. If you remember the solubility rules, all salt or sulfate are soluble, with the exception of calcium, barium, silver, and lead. So barium sulfate, lead sulfate, silver sulfate, they are insoluble. So you are forming a precipitate. So a precipitate is a solid substance formed when two aqueous are mixed together. A precipitate is a crystal or a solid substance formed when two aqueous solutions are mixed. So by mixing the barium chloride and then the sulfuric acid, you are getting barium sulfate, which is being shown or which is being seen as a white precipitate. Look at it. It has settled down. So you can see a solution on top and the crystals are down. The crystals you are seeing down there, the solid sample you are seeing down there is barium sulfate. The HCl is what is on top of it. So if I should decant this one, the substance underneath is the barium sulfate. So when you carry out the test, what you will see will help you to conclude on which ion is present. The observation is what is going to guide us to know which ion is present in the solution we are testing for. So the white PPT that we are seeing there is not a cation we have identified. Because when we are identifying a cation, there should be either dilute ammonia or dilute sodium hydroxide. So these two solutions are used in identifying cations. When we come to the anions, I'll give you the kind of solution that we use there. In fact, barium chloride is used in testing for anions. When we get there, I'll throw more light on that. Yes, sir. So when it comes to the text, we have a test column, observation, and then inference. Inference is more or less at the conclusion or the ions you are suspecting to be there. Now, among the cations, the ammonium cation is the only cation that gives off a gas when dilute sodium hydroxide is added. The cations do not give off gas except ammonium cation. For ammonium cation, when you add sodium hydroxide solution to the test solution and you warm or you heat, ammonia gas is evolved. Ammonia gas will come out. Now, based on the color of the gas and the odor and the effect on litmus paper, we'll be able to identify the ammonia gas. This is to say that when you are performing a test and you suspect a gas, then 3 things must be done on the gas. You have to smell the gas to know the odor. Then you have to observe the color of the gas. Whether it is colorless, whether it is blue, whether it is yellow, you have to observe the color of the gas. And then the third thing is to test for the acidity of the gas, whether it is an acidic gas, basic gas, or neutral gas, using wet litmus paper. The litmus paper must be wet or damp, because when it is dry, the gas will not have any effect on it. So you have to tape the litmus paper in distilled water for it to be wet before you bring it near the gas. And please, if you are testing for the gas, assuming this is your test tube and the gas is coming out and this is your test paper, you just hold the test paper close to the mouth of the test tube so that the gas will pass over it. So that if the gas is acidic gas, then it will turn blue litmus paper red. And if it is a basic gas, then it will turn red litmus paper blue. We don't dip the litmus paper into the test tube. If you do that, it is wrong. Because if you dip the litmus paper into the test tube and the inside of the test tube is acidic, then it will not be the gas which is acting on the litmus paper, but the solution in the test tube which is acting on it. So we don't dip the litmus paper into the test tube. We hold it over the test tube to test for the gas. Also, if you want to smell the gas, assuming the gas is coming out from this test tube, you hold the test tube some few centimeters away from your nose. Then you wave the gas into your nose. You don't bring the sniff. You don't bring the test tube close to your nose and sniff the gas. Because if the gas is poisonous, you'll be harming yourself. So you hold the test tube some few centimeters away from your nose, and then you wave the gas into your nostril in order to smell it. So that's the technique you have to know today. Now, so let us assume that the solution given to us, the test solution that I want to identify the ions in it, is labeled C. We are just assuming that the test solution is labeled C. So solution C plus dilute sodium hydroxide aqueous. That's the test. Plus heat, or if you like, warm. I've given you a clue that it is only ammonium ion that when you add dilute sodium hydroxide, you warm or you heat. The rest, we don't do that. It is only ammonium ion. Now, when you add a dilute sodium hydroxide and you heat, there's going to be a colorless gas with a pungent smell. It smells like urine. So a colorless gas with a pungent smell will be evolved. Now the gas turns white, red litmus paper blue. The gas is ammonia. And ammonia gas is basic. That is the only basic gas known within our parameters. The only alkaline gas that will be coming across in the SSL level is ammonia. So that gas can turn wet, red litmus paper blue, indicating that it is alkaline. And that one alone confirms that ammonia is present. Therefore, ammonium ion is there. So under the observation column, it will be recorded that a colorless gas with a pungent smell, or if you like, urine-like. It smells like urine. Like John saw at the Sobisa. Urine-like smell. The gas turns wet, or if you like, I use the word damp. Damp red litmus blue. Now, the gas plus conch HCl will give you white fumes. White fumes will be formed. So under the inference column, we state that the gas is ammonia. Therefore, NH4 plus confirmed, or present if you want. So this is the test. This is the observation. It is the observation that is leading to the inference, or if you like, the conclusion. Now, for the NOVDEC, they can give you the test, then they leave the observation column blank, then they give you the inference. You should be able to look at the test, the inference, and give the observation. That one, you are not going to perform the experiment. The NOVDEC type of this thing, you will not perform the experiment. So they'll give you the table, and then they'll leave some spaces out, then you fill it. So if you don't have an idea about a thing, then you don't know what you are going to write there. So sometimes they'll give you the test, the observation, and then the inference will not be there. So based on the test and the inference, you should be able to provide, based on the test and the observation, you should be able to provide the inference. Please, is it well understood? Any question?
Yes, sir.
Any question? All right. So this is the entire test on ammonium ion. And please, what we are doing here is not magic. It is a chemical reaction that is occurring. So here, the ammonia gas involved, if you have an ammonium ion and you add sodium hydroxide to it, then you are going to get ammonia gas plus water plus a salt. 3 products will be obtained. 3. If you know the anion here in the ammonium, then the anion will be added to the sodium to give you the salt. So if this one were to be ammonium chloride plus sodium hydroxide, you are going to get ammonia, water plus sodium chloride. So the ionic equation here is the ammonium ion plus the sodium hydroxide giving us ammonia, water, and then the ammonia, the sodium ion. So it is this gas that is liberated, and that is what is observed here. So you see the gas will come out, it is colorless, but has a pungent smell, or urine-like smell. Sometimes they say choky smell. When it comes to the odor of substance, we lack a lot the vocabs there.
Sir.
Yes.
Please, I'm slightly confused. Please, what did you say the solution C is?
The solution C is a solution that has been given to us. We don't know what is in it.
Okay.
So
would it be like a mixture of something, or to just be a solution you have no idea about?
Yeah, it can be a mixture.
Okay.
It can be a mixture.
Okay, then you add the dilute sodium hydroxide,
yes,
which is the reagent, right? Okay. And then you heat it.
Yes.
Then a gas will be evolved. Okay, I understand that part. A gas will be evolved. Then you're saying the gas that will be evolved will be ammonia.
Yes.
Based on the characteristics it brings out, it to be ammonia. Okay. So how are you able to confirm that you get the ammonium ion?
Yes. So that's why we are saying that among the cations that we are going to study, it is only the ammonium cation that will give off that gas.
Oh, okay.
Yes.
Okay.
All the rest will never produce ammonia gas when sodium hydroxide is added.
Okay. Okay.
You get a point?
Yes. So anytime, like, let's say I'm performing an experiment and then I see ammonia gas, I shouldn't think plenty. I should know that it's ammonium.
Yes, you should know that it's an ammonium compound.
Okay.
I don't know whether that preparation of gases.
Yes.
And the state of matter.
Yeah, we have.
And you can cross-check. In producing ammonia gas in the lab, you need ammonium chloride plus calcium hydroxide solution. In place of calcium hydroxide, you can use sodium hydroxide or even potassium hydroxide. And then you heat it. The ammonia gas will be heated. The ammonia gas will come and can be collected.
Okay. Okay.
Do you understand it?
So, sir, please, yes, I do. Please, based on the two regions you've given us, is it like every cation with its particular region is supposed to go with? So you cannot go and use ammonia for this particular cation, and you cannot go and use sodium hydroxide for this particular cation.
In fact, for the ammonium ion, we don't use the dilute ammonia for it. The only reagent we use for the ammonium ion is the dilute sodium hydroxide, full stop. As it comes to the rest, that will be considering soon. That one, we add both the sodium hydroxide solution and then the dilute ammonia. We'll be using the two. We'll be using
so for the rest, you mix the two regions.
Hello?
I'm saying that for the rest, you mix the two regions.
No, we'll add them one at a time and then observe and record what we've seen.
Oh, okay. Okay.
We don't do two at the same time. We add it separately.
Okay.
Do you understand it?
Okay. Yes, I do. So please, the ionic equation thing we're talking about, what was it?
Oh yeah, so what I was trying to say there is that what we are observing here is not a magic. Actually a chemical reaction which is occurring. And out of that reaction, we are seeing what we are seeing, or we are observing what we are seeing.
Okay.
So when you add the sodium hydroxide to a test solution, that contains ammonium ion, then definitely the ammonia gas will come out. Sometimes you don't even need to heat it. I wish you are even close to me so that I could do it for you to smell it. It is not possible for you to smell through the line. So when you mix the sodium hydroxide with the ammonium ion solution, even in the cold, the gas will be evolved. But when you warm it or when you heat it, it comes out more. Comes out. And then it can even, diffuse into the entire room. Yes. So that's the test for the ammonium ion. And please, what in here serves as the basis for what medical laboratory technicians do. So you see that when you go to the hospital, they ask you to bring your either stool or urine or saliva or blood sample, and then they conduct a test for a particular ailment or disease. Like if you're having malaria, they'll take a sample and they will conduct a test on the sample. So from the test, what they will see, then based on that, they'll draw their conclusion. The observation that will come out will help them to know whether you have the malaria parasite or not. So this serves as the basis for that. So that when you add this reagent to this sample and this does not occur, then this is not there. So like this one, if you add sodium hydroxide to a test solution and there's no gas evolved, no odor, no precipitate formed, that means ammonia is not there or ammonium ion is not there. Because once you are adding the sodium hydroxide and you are warming, you should be expecting ammonium ion. So when you do it and there's no gas involved, there's no pungent smell, there's no urine-like smell, that is an indication that ammonium ion is not in that test solution. It is absent. We call it a negative test. But when it is there, then it is what? A positive test. That's why when they test for you, they test your sample and the malaria parasite is there, they say it is positive. It is not there, then they record that it is negative. It is not present. So this is the basis for that. Any other question? No. Chief, are you there?
Yes, sir.
That's right. Mami Alita, can I continue?
Yes, sir. Please, you can.
Okay. Hey, my man, Bob. Yes. All right. So we are moving on. Can I rub this one? I hope so.
Yes, sir.
Okay. Now, the next four ions among the cation, they seem to be difficult, but they are not. Among the cations, these four, Zn2 plus, Al3 plus, Pb2 plus, Ca2 plus. They seem to be confusing, but they are not. They are not. When you add sodium hydroxide solution to a test solution that contains any of these cations, you are going to see a white PPT, white precipitate will be seen. Zn2 plus, Al3 plus, Pb2 plus, Ca2 plus. On adding dilute sodium hydroxide, you will see white PPT. And here we add in drops and then in excess. Sometimes in drops, a PPT will be formed. But in excess, when more is added, the PPT will be soluble. So on adding the reagent, you add it in drops, followed by excess. So in drops, when you add the sodium hydroxide, Zn2 plus, Al3 plus, Pb2 plus, Ca2 plus will give you a white PPT. So you have so many ions being suspected. Now, when you add in excess, if zinc is there, or aluminum, or lead, they'll be soluble. This three is soluble in excess sodium hydroxide solution. Zn2 plus, Al3 plus, and Pb2 plus, they are soluble in excess because they are amphoteric. They are soluble in essence because they are hot. Amphoteric substances. Do you know amphoteric substances? Who knows it? Who can tell me? Who can help me? Amphoteric substances.
So
Yes, sir. No.
it can react with both acids and bases.
Exactly. Amphoteric substances can react with both acids and bases. So Zn2 plus, Al3 plus, Pb2 plus, because of the amphoteric nature, when you add sodium hydroxide to them in excess, the PPT will dissolve. The PPT is soluble because they are amphoteric. But if it is Ca2 plus, the PPT will not dissolve. Ca2 plus is not amphoteric, so it will not dissolve. It will remain there. Thank you. Now, we can qualify the white. And if the white is qualified, it narrows the scope. Now, these two, Zn2 plus and Al3 plus, when you add the dilute sodium hydroxide in drops, you form white gelatinous PPT. White gelatinous PPT. So solution C plus dilute sodium hydroxide in drops. I'll show you what we mean by drops. And then you form white gelatinous. Let me just write gel. Gelatinous PPT in drops. Then at the inference column, you say that Zn2 plus or Al3 plus percent.
So I have a question.
Huh?
I have a question.
Go ahead.
So does this mean that this is the preliminary test?
Yes, it is a preliminary test.
Because, okay.
It's a preliminary test. You are using sodium hydroxide.
Sir,
Yes, sir. Oh, yes, madam.
sir, please, what topic is this test for ions under?
The topic is identification of cations and anions. It's under practicals.
Okay. Okay. Okay.
Usually,
So it will be in the other textbook, the Kosoko.
yes, usually we treat it under solubility. So you see that I was trying to refer you to the solubility rules.
Yes.
Uh-huh.
Yes.
Yeah.
Okay, thank you.
Right. So that is in drops. Then you said that, and then in excess, please, when you are adding the reagent in excess, you want to find out whether the precipitate will be soluble or not. You don't record anything strange by saying that the PPT is soluble or insoluble. That is in the essence. I'll be illustrating that one for you to see. Now, when you add sodium hydroxide in excess, would the precipitate be soluble or insoluble? Who can help me? Would the precipitate be soluble or insoluble?
For which ion?
For what we have done here.
It will be soluble.
Why?
Like you said, from zinc to lead are soluble in excess sodium hydroxide.
Yes, sir. That's exactly so. Because earlier on we said that for Zn2 plus, Al3 plus, and Pb2 plus, they are amphoteric. So they'll be soluble in excess sodium hydroxide. So it means that in excess, they record here, PPT soluble. And both of them will be soluble. So record both of them. Zn2 plus or Al3 plus percent. So it means that we cannot use dilute sodium hydroxide to differentiate between Zn2 plus and Al3 plus. We cannot use that. Now, okay, let me just do that illustration, then we see what it means.
Sam. Yeah. Sam,
Yes.
please, could you like go back one step? So I understand to the point where zinc, aluminium, and lead will both be soluble because they are amphoteric.
Yeah.
And now we are trying to narrow the scope. And you said that only zinc and aluminium amongst those three will give us a white gelatinous precipitate,
Huh?
right? Okay. Now you are saying that when we add excess sodium hydroxide, they will all dissolve.
Yes.
I'm a bit stuck at that point because it has confused me a bit.
Oh, why
Like,
is you? Because you have stated everything clearly.
hey, do you know I had a question? I've even forgotten the question.
Let's start writing down, okay?
If it comes back again, I'll ask him.
No problem.
Because it was
Okay. So see.
Please, sir.
Yes, sir.
There is a table in the Kosoko.
Yes. You see that one in there. Yeah.
Okay, yes, sir. Thank you.
All right. Now I have a test solution here. So the test solution will be provided to you. You don't know what is there, but they will instruct you. Add dilute sodium hydroxide in drops and then in excess. So that is the question. That will be provided with sample C to about 2 cm cube of sample C. Add dilute sodium hydroxide in drops or in excess. So this is about 2 cm cube. And please, I don't expect you to go and look for measure cylinder to measure 2 cm cube. Just estimate something. Sometimes you even use a smaller test tube like this. Don't pour the test reagent plenty, the test solution, don't pour plenty. About 2 cm cube is enough. So just do some estimation for the 2 cm cube. Now I'm going to add sodium hydroxide. You can see it on it. In drops and then in excess. And drops, don't go and look for dropper. I beg you, just pour a little without shaking. Don't shake the test tube, just add drops. This is drops. Now look at the solution in it. Can you see from that angle? You see it? Have you seen how it is? That is jelly-like. That is jelly. We have another one which is chalky. Compare this one to this. You see some difference. You see this one? This one is jelly-like, but this one is chalky. It's like chalk particles in water. So when the thing is jelly, then it is this true. They will give you this kind of thing. Now let me add in excess. Excess you add proper, as if the solution you don't buy. You add, and then shake. Sometimes you have to even place your thumb at the mouth of the test tube and shake well. Look at it. What has happened? Please, can you see from there?
Yes, sir.
You can see?
You can see.
What has happened? The PPT has dissolved. It has dissolved completely. Have you seen it? Michelle? So at this point, you cannot conclude which of the cation is there. Because Zn2 plus and Al3 plus, both of them will form a white gelatinous PPT in drops. But when you add the sodium hydroxide reagent in excess, both of them will dissolve. Because of that, we will write both of them there. Please, if you record only one, if the examiner is scoring one for each, you score only one. It is the two ions that you are suspecting. At this point, you cannot differentiate which one is there and which one is not there. Great. So this is the first part for the Zn2 plus and then the Al3 plus. Now the next one, you are going to use the aqueous ammonia. I told you that we use the two reagents. So solution C again, plus this time around, dilute ammonia solution. in drops. This is going to give you the same white gelatinous PPT. Yes, sir. White gelatinous PPT. It's the same test for ZN2 plus or AL3 plus. So either this or this is present. And please, when you are doing the recording, it should be in line. This is drops, so it should be in line. This is in essence, even though I have not drawn any line dividing them, like they are at par. So if this one were to be here, if this PPT were to be here, I will not put this one right under this because in drops has fall to this level. So it will still just be in line with the SS. Are you getting it? Because the examiner should read the thing to make meaning out of it. You should know that in drops, this is the observation. In SS, this is the observation, and this is the conclusion. So it should be at par, it should be in line. So, and then in SS, one is soluble, one is insoluble. In SS, if ZN2 plus is there, the PPT is soluble. PPT soluble. If ZN2 plus is there. Now, if the PPT is insoluble, PPT did not dissolve, then that one is AL3 plus, which is present. Watch us here. Now, let me illustrate that one. I have my test reagent here. It's the same one that I used at first, the same test reagent. So I have poured another portion. This is about 2 cm cube. Yes. Now I'm adding ammonia solution. There's the ammonia, dilute ammonia solution, aqueous, in drops. In drops. So I add without shaking. That's the drops. Can you see the jelly-like? That's the jelly-like. You can see it clearly. Now I'm going to add in essence. When I added the sodium hydroxide in essence, we saw what happened. Now I'm adding in essence. Tell me whether it is soluble or insoluble. Look at it. I have actually added. You saw it. Look at the level from where we started from and where we have reached. I can continue to add. Is it soluble?
No, please.
It is insoluble. So if it is insoluble, then which ion will be there?
Aluminum.
Yes, Bob.
The aluminum ion.
Aluminum ion. So because the PPT is insoluble in SS, we are concluding that the ion present is aluminum Al3 plus. It's aluminum ion. If it were to be soluble, then we are concluded by saying that it is Zn2 plus. You get the point? So we can use dilute ammonia to differentiate between Al3 plus and Zn2 plus. One is soluble in SS, One is insoluble in excess dilute ammonia. You get the point? Yes, sir. Now, don't forget, what we are doing here too is a chemical reaction. It is a chemical reaction. What is happening here is that if you add sodium hydroxide to a solution that contains zinc ions, you are going to form zinc hydroxide. This one is solid. It is insoluble. You are going to form this plus Na plus. You can balance the equation to that effect. This is the reaction occurring there. If it is aluminium that you are using, then you are going to produce aluminium hydroxide. Aluminium hydroxide. And that one too is insoluble. To give you this aluminium hydroxide, zinc hydroxide. That is the reaction which is occurring there. In fact, plus Na plus by ionic equation. Then this precipitate, this solid, or that of the aluminium, when you add excess sodium hydroxide, it will react with it to form a complex. And the complex is soluble. That is why on adding in excess, this PPT dissolves. That one you can write the balance equation to that effect. So when this PPT dissolves to give you the complex, which is soluble in water, you see the PPT disappearing. It's a complete reaction that has occurred there. When it comes to the ammonia, please, the ammonia solution also contains hydroxide ions. The ammonia solution, it contains hydroxide ions. In actual fact, when ammonia is dissolved in water, you're supposed to get ammonium hydroxide. So that when the ammonium hydroxide breaks down, dissociates, then you get ammonium ion and then hydroxide ions. So the hydroxide ions from the ammonia is what is also reacting with the zinc and then the aluminium to give you the gelatinous PPT that we saw. But then we don't write ammonia solution as this, as ammonium hydroxide. We don't write it this way. When you dissolve ammonia in water to get this, we don't write it this way. Because ammonia is highly soluble in water. Because of the high solubility of ammonia in water, we just write it ammonia aqueous. But when it comes to the reaction, it is the hydroxide from the ammonia that will combine with the zinc to give you zinc hydroxide. It is the hydroxide from the ammonia that will combine with the aluminium to give you this. But the ammonia solution is just a weak base. It's a weak one, not strong as the sodium hydroxide. So that is the reaction equations to that effect. Yes, sir. Any question? Hey, Mami Edima, are you there?
Yes, sir. I'm trying to follow, but then this one was breaking. You were breaking, so.
Oh, my line is breaking. Eh?
Yeah.
Oh, but you are not alerting me. So you didn't get anything, eh?
I don't know whether it's from my side because they are saying my internet something is unstable, and the wind is blowing. So I'm guessing it's from me. Like it's this one.
Too bad. Is it happening to the rest?
But I'm following.
You are following, okay. But the rest, I hope the line is okay. Or it's also breaking at your end?
It's okay.
It's okay.
Okay,
That's fine.
right. Now, let me move on to the lead and calcium. Pb2 plus and then the Ce2 plus. Now, if the test solution contains lead or calcium, that one will be chalky. That will give you white, chalky PPT, white chalky precipitate. Yes, sir. How are you? So that one, you see it as chalk particles in solution. So this will be giving you Pb2 plus or Ca2 plus. That is 8 drops. 8 drops. And then in essence. Now in essence, if you add the sodium hydroxide in essence, if you are suspecting the two cations, will it be soluble or insoluble? Will it be soluble or insoluble? And why? Yes, sir, I'm listening.
So can you please repeat your question?
Huh?
Can you please repeat your question?
Yes, what I'm saying is that I've added dilute sodium hydroxide reagent to a test solution, and there's white chalky PPT. So I suspect Pb2 plus or Ca2 plus to be present. My question is that if I add the excess sodium hydroxide, to it, what will I expect to see? Maybe let me put it this way. What will I expect to see if calcium is there? Will the PPT be soluble or insoluble?
So,
Yes.
it will be insoluble in calcium but soluble in lead.
It will be insoluble with calcium,
Yes,
but soluble with.
lead.
Is there any reason to that?
I don't know.
You don't know, so you're just saying something.
No, I learned it some time ago. So I'm trying to use past knowledge, but I don't remember what the explanation was.
Yeah, we gave a reason earlier. So I'm expecting you to explain based on that reason that we gave earlier.
Sir, please, can you remind me? I don't think I remember.
Oh, okay. Who can tell me? Chief?
Yeah, please, I'm not really sure. I'm still thinking about it.
Yo. King?
So please, I don't know.
Debbie. Debbie. Bob?
So because the the lead is amphoteric, dissolve.
Big. It is because it is amphoteric. So if lead is there and you add the sodium hydroxide in essence, it will be soluble. Look at this. I'm having my test reagent, or sorry, test solution. The reagent here is sodium hydroxide. I'm adding in drops. See. You see the difference? This one is chalky. See. You see, when it is gelatinous, it is clear. Gelatinous, it is thick. And slimy, sort of. But this one, look. When you shake it by it to come back. When you allow it to settle, the particles will go down it, and then there will be a colorless solution on top. I'm adding in essence. What ion is in the solution, in the test solution? Look.
The lead.
It is lead.
The lead ion.
You see that thing? So when you add in excess and the PPT dissolves, then lead is present. So in excess, PPT soluble. Soluble. Here will be PP2 plus present. But if it were to be calcium, like the PPT will be what? Insoluble. PPT insoluble. Insoluble. Then that one you say that it is Pb2 plus A. Ca2 plus, which is present. Yes, sir. Any question? Any question? No question. Thank you, sir. Then we now use ammonia on it and see what will happen. So solution C plus dilute ammonia, NH3, aqueous, in drops. In drops. And that's going to give us white chalky PPT. Chalky PPT. And please, ammonia is not able to precipitate calcium. Ammonia is too weak to precipitate calcium. So when you are using the ammonia, and you are getting the white PPT, then it is lead, which is there. If it is calcium, there will be no PPT. If it is calcium, there will be no PPT. So white PPT, white chalky PPT will be Pb2 plus present. So if you add in drops and there's no PPT, then that one is calcium. It's calcium. And then in excess, the PPT is insoluble. PPT insoluble. It is saying Pb2 plus, which is present. The PB2 will be insoluble. Because the ammonia solution is a weak base. It's a weak base. So that one will not be able to precipitate the calcium. So the calcium will not give you any PPT. There'll be no observable reaction. You will not see anything. The solution will just be there like that. That means that it is calcium. And even that, before you get to the addition of ammonia, you know which element is there or which ion is there. Because we can use sodium hydroxide to differentiate between lead and calcium. We can use that one. But we cannot use sodium hydroxide to differentiate between zinc and aluminum. With the lead and the calcium, we can use the sodium hydroxide because one is soluble in excess and one is insoluble. So that can be used. You got a point?
Sir,
Yes.
please, are you trying to tell us that in identification of lead and calcium, there are two ways of identifying them based on the two reagents?
Yes.
Oh, okay. Okay.
No, not that there are two ways of identifying them, but using the reagent, sodium hydroxide and ammonia, we can actually differentiate between those ions.
Okay. Yeah, so like in the case of the calcium, it was what, zinc and aluminum, where we needed like both of them to get to the end of the reaction. It doesn't like occur here. You get that? Do you get what I'm trying to say?
Yeah, if I understood what you're trying to say, you are trying to say that for the aluminum and then the zinc ions, that one, when you add the sodium hydroxide, you cannot differentiate between them.
Yes.
So you add the ammonia.
Yes.
Yes. It is the ammonia solution that you can use to differentiate between the two. Yes.
Thank you.
Yes. But even though we can use the sodium hydroxide and the ammonia to differentiate between them, we still have a confirmatory test for each of them. The sodium hydroxide and the ammonia solution are being used as, preliminary test. So with the preliminary test, it gives you varied, ions that are present. But you can see that on adding in drops and in excess, we are able to distinguish between two ions. Apart from that, we can still perform a confirmatory test that will identify only one particular cation. We'll come to that later.
So say, are you trying to tell me that all these things we are doing are all preliminary tests?
Yes.
Oh, wow.
These are all.
Okay, so you are saying that for the confirmatory test,
Yeah,
like you don't have to go through a long process like this. It will give you the answer.
your line was a bit scratchy, so I couldn't get you well.
Sorry. Can you hear me? So I was saying that, so for the confirmatory test, you will not have to go through a process. You just do something and then you'll be able to tell that this one is zinc or this one is this or this one is that.
Oh no, in fact, the confirmatory test comes after the preliminary test. After doing the preliminary test, then you now come to the confirmatory test. After doing the preliminary test, for example, by using the ammonia, we have concluded that lead is present. Then the question can ask you that, perform one confirmatory test on the ion you have identified. So here, the question is not directing you as to what to do, but you should know the confirmatory test for lead and perform that test on the lead.
Okay, sir.
Yes, but sometimes the question will still direct you that add so and so reagent. Then you should know that once you have already identified that it is lead which is present, and the question is further asking you to add some other reagent, then that reagent is just going to confirm the lead. Understood?
Yes, please. Thank you.
Any further question? Edima, are you now okay? Or it is still breaking?
Oh, I'm fine. I've switched, so I'm fine.
All right, great. Now, so you see that the ones that I was saying that they seem to be difficult after all are not difficult. The zinc, aluminum, lead, and calcium. They seem to be difficult, but they are not. From what we have done, you realize that they are not difficult. And in fact, if they don't qualify the white, assuming they are saying that it's white PPT as a preliminary test, you have added dilute sodium hydroxide and you are forming white PPT. This one, they have not qualified the white. If you are performing it, fine. Then that one, you will qualify the white. But for the NOVDEC, if they just write there, white PPT, without qualifying the white, then in that case, you should be suspecting all the four there. This, or that. That one, all of them will give you white. But when you qualify the white, then like I said, it narrows the scope to this two or that two. So, now good. As for the last three, it is the easiest because by their color, you will know them. Iron 2 is green in color. Iron 3 is brown in color. In fact, reddish brown in color. Copper is blue. Copper, it is blue. So for these three, they are the simplest ones. Because once you see the color, you know that it is this ion that is there. It is very simple. And there's no competition too. And that is one of the characteristics of the transition metals. They form colored compounds. They form colored compounds. So the iron 2, iron 3, and copper, they are all transition metal ions. And that is why their solutions are colored. So when you add the sodium hydroxide in drops, if it is iron 2, you are going to get green gelatinous PPT, which turns brown. Okay, so the PPT is insoluble in essence. PPT insoluble. Which turns brown, turns reddish, let me qualify it. Reddish brown on standing. On standing. And the inference is Fe2 plus. Fe2 plus. Nothing new. Now, the iron 2, when you add the excess sodium hydroxide, will be insoluble. But as time goes on, the green gelatinous will turn to reddish brown because iron 2 is highly unstable and can therefore undergo oxidation quickly to iron 3. That's why we said that on standing, it turns to reddish brown PPT due to the formation of iron 3. And it can quickly oxidize fast to iron 3. So they give you that. In aqueous ammonia, the same observation. The same observation. Green gelatinous PPT insoluble in essence. The same observation. When it comes to the ion 3, that will give you reddish brown. Reddish brown, gelatinous PPT. That's ion 3. The PPT is insoluble in essence. Ammonia, if you are using ammonia instead of sodium hydroxide, the same observation, the same thing over here. Direct, no change. No change. Yes, sir. Any question? Then copper. For copper, when you add the sodium hydroxide in drops, it will give you blue gelatinous PPT. Blue gelatinous PPT. And the PPT is insoluble in essence. Blue gelatinous PPT. PPT insoluble. That is Cu2 plus. Cu2 plus. No competition. It is not this or that. The same thing. The same thing. No competition. But then if you use ammonia, ammonia in drops will give you light blue gelatinous PPT. Light blue gelatinous PPT. When you add in excess, the PPT dissolves. You see the solution for copper? You can see it. It is blue already. You have not added anything. The thing is already blue. So this one, too, if you cannot record it, then what again? So you add ammonia in drops. That's the drops. It gives you light blue gelatinous PPT. Have you seen it? Now, but when you add the ammonia in excess, the PPT dissolves, forming a deep blue solution. Have you seen it? The PPT is soluble, forming deep blue solution. Just very clear deep blue solution. Have you seen it? Yes. So for the copper, yes. In drops, when you use ammonia, will give you light blue gelatinous PPT. In essence, PPT soluble. PPT dissolves, forming a deep blue. Oh, I don't know that's on trouble. A deep blue solution. And that confirms the copper 2 ions. Copper 2 ions. Yes, sir. Cool job. Please, is it difficult? All right. Any question? Otherwise,